Right now, the nothing in this room is pushing on you with the weight of a 10-ton truck on an area the size of a small table. So why aren't you crushed? Why don't windows implode? And why does a simple vacuum suddenly turn that invisible squeeze into violence? Look at the air in this room. Not the dust, not the smell. The air itself. We treat it like nothing, like the default setting of the universe, like a free bonus we don't pay attention to. But physics doesn't let you do that, because that nothing is heavy, and it is pressing on you right now with a force that, if you convert it into something your instincts understand, sounds completely insane. Here's the number. Atmospheric pressure is about 101,000 newtons per square meter. That's 101,000 push units on every square meter of surface. And if you translate that into weight, it's roughly the weight of a 10-ton truck on 1 square meter. 1 square meter. About the size of a small table. So take a table-sized patch of your ceiling. The air above it is pushing down with about 10 tons of force. Now look at your whole ceiling. It's not 1 square meter. It's many. So the total force is not 10 tons. It's tens of tons. Sometimes over 100 tons, depending on room size. And yet, the ceiling is not collapsing onto your head. So either physics is lying, or your intuition about what pressure means is broken. Now the first thing your brain tries to do is picture a pile of air sitting on top of your room like a stack of mattresses. A column of air, miles high, crushing everything at the bottom. That picture is not totally wrong. The air really does have weight, and gravity really does keep it from floating away. If gravity disappeared, the atmosphere would spread out into space. So yes, there is air above you. But the crushing mattresses picture sneaks in a hidden assumption that pressure is a one-way thing, downward, like weight. And that's the trap. Pressure is not a downward force. Pressure is not a top pushing on a bottom. Pressure is what happens when something pushes on you from all sides. All sides. Up, down, left, right, and even from inside you. So if you only remember one sentence from this first part, make it this. Pressure isn't a direction. Pressure is a surrounding. Now let's make the problem feel real, because otherwise it stays as a cute number. If 10 tons per square meter is real, why don't windows implode? A window is basically a thin sheet separating inside air from outside air. If the outside is pressing with 10 tons per square meter, shouldn't your glass bow inward like plastic wrap? Shouldn't it crack? Shouldn't your whole house be slowly getting squeezed like a soda can? And if you want a creepier question, why don't you implode? Your body has surfaces too. Your skin, your lungs, your eyeballs. Air is pressing on all of it. 10 tons per square meter. If that's true, you should be some kind of biological pancake. But you're not. You stand up. You walk around. You don't even feel it. So maybe you say, okay, fine. The air is pushing, but I guess we're strong. No, that's the wrong answer. Because you are not strong enough to hold up 10 tons per square meter with muscle. Your bones are impressive, but they're not built like submarine hulls. Also, your body is soft. A lot of you is basically water in a bag. You don't resist pressure by being rigid. So something else is happening. Something more subtle. Here's another thing that seems to contradict the whole story. We can make pressure do work in a dramatic way. A suction cup sticks to a wall, and you can hang a whole object from it. A vacuum-sealed jar lid is hard to open. A syringe works because pressure differences push the plunger. A straw works because the atmosphere shoves the drink up into your mouth when you lower the pressure in your mouth. And the classic brutal demo. Take an empty metal can, put a little water in it, heat it so steam fills it, then cool it fast. The can crushes inward like it got hit by a giant invisible fist. That's not a metaphor. That's pressure. That's the 10 ton per square meter reality showing itself. So we have a strange situation. 1. Pressure is huge. 2. Usually we don't notice it. 3. But if you remove air from one side, suddenly everything gets smashed. That last point is the key. It tells you the story is not air is pushing, the story is difference in pressure is pushing. Because when the can crushes, it's not that the outside pressure suddenly got bigger. The atmosphere didn't change. What changed is the inside pressure got smaller. The can stopped being pushed outward from within, and the outside push won. So why doesn't your room get crushed? Why don't you get crushed? Because you are not a can with nothing inside. Your room has air inside it. Your body has pressure inside it too. And as long as the inside pressure matches the outside pressure, there is no net crushing. There's pressure, yes, but it's balanced pressure. Balanced doesn't mean zero. It means equal in every direction. Think about holding a book in your hands. That's an unbalanced force. Gravity pulls down, your hands push up. If your hands slip, the book accelerates. Something happens. But imagine being deep underwater, where the water pressure is large. The water presses on your arm from every side. Front, back, left, right. The pressure is enormous, but your arm doesn't fly off in a direction, because the pushes cancel. Now here's the part people miss. The same cancellation is happening in air. It's just harder to feel, because air is light, and because your body is already tuned to it. You were born at the bottom of this invisible ocean. Every cell grew up with that squeeze as the normal condition. Your fluids, your tissues, your lungs, they're all pressurized systems, not consciously, just physically. So the mystery becomes sharper, more precise. It's not why aren't we crushed by air pressure, it's what exactly is pushing, and how does the balancing actually happen? Because balanced from all sides sounds like a slogan until you face the awkward details. For instance, if pressure pushes in all directions, what is it pushing with? What is doing the pushing? Is it the weight of air above you? But weight points downward, so why sideways pushes? Why upward pushes? And what about a vacuum? People say the vacuum sucks, but is it? Or is that another intuition trap? If vacuum sucks, why can't you build a suction machine that pulls with infinite force? Why does everything have a limit set by atmospheric pressure? Why does a suction cup only pull as hard as the atmosphere can push? And here's one more question that sounds simple but is actually the whole topic. What changes when the air is gone? Not in a poetic way, in a mechanical way. If I could magically delete the air from your room, instant vacuum, what happens first? Do the walls explode outward? Do your ears pop because your body pressure is higher? Do the windows fly out? Does the floor jump up? You can't answer those questions honestly until you understand what pressure really is physically, not as a definition in a book, but as a mechanism, a microscopic cause. So that's the problem we're going to solve. We're going to rebuild pressure from the ground up, literally from particles hitting things. We're going to see why 10 tons per square meter is real and yet harmless until it isn't. And we're going to end up with a new picture of daily life. You are not walking around in emptiness. You are living at the bottom of an invisible ocean, and you've never felt the water because you're made of water too. So what is pressure, physically? Not the dictionary definition, the mechanism. Because if you open the hood, it's embarrassingly simple. Pressure is made of impacts, little punches, countless, tiny, stupid punches. Air is not a continuous jelly that leans on things. Air is a swarm of molecules, mostly nitrogen and oxygen, zipping around at hundreds of meters per second. At room temperature, a typical molecule is moving roughly like a rifle bullet, not in one direction, but in every direction, changing direction constantly because it keeps crashing into other molecules. Now picture a wall. From your point of view, the wall just sits there, quietly minding its business. But from the wall's point of view, it's being machine-gunned by molecules all day long. Each time a molecule hits the wall, it bounces. And when it bounces, its momentum changes direction. That change of momentum means the wall had to exert a force on the molecule. And Newton won't let you cheat. The molecule exerts an equal and opposite force back on the wall. That average force, spread over an area, is pressure. So pressure is not air weight. Pressure is momentum transfer per area per time. It's bookkeeping for 1 trillion collisions you don't see. And this instantly answers the weirdest part. Why does pressure push sideways? Why up? Why not just down? Because the molecules are not politely falling straight down like rain. They're not stacked like bricks. They're flying around randomly. Some hit the wall from the left, some from the right, some from above, some from below. The wall doesn't care where they came from. It just feels impacts. And because the swarm is basically symmetric in all directions, no preferred sideways direction in a calm room, the impacts come equally from every direction. That's why pressure, at a point, is the same in all directions. That's why it feels like a squeeze, not a shove. Now, gravity is still there. Gravity makes the air denser near the floor than near the ceiling. So pressure is slightly higher at your feet than at your head, but the difference across your body height is small compared to the total. You don't notice it. You know what you would notice? If the air stopped hitting you from one side, that's when pressure stops being a quiet squeeze and becomes a brutal net force. This is why the word vacuum confuses people. Vacuum doesn't pull. Vacuum is just the absence of impacts. No molecules, no punches. So when you say the vacuum sucked the air out, what really happened is, The air on the other side pushed the air out. When you stick a suction cup on glass, nothing in the cup is pulling the glass. The cup isn't a little octopus with muscles. All you did was push some air out from under the cup, reducing the number of molecular punches on that side. Now the outside air is still punching the other side of the cup at full strength, so the cup gets pressed onto the glass. Pressed, not pulled. And this is why suction has a hard limit. You can't get more suction than a perfect vacuum. Once you've removed basically all the air under the suction cup, that's it. You can't remove less than nothing. At that point, the maximum sticking force is just atmospheric pressure times the area of the cup. Period. Nature has a ceiling. This is also why the crushed can demo is so violent. When you cool the steam, the number of molecules inside drops dramatically. Inside pressure collapses. Outside pressure doesn't change. Now the net force is inward, and the can folds because it's thin. If you want a beautiful mental picture, imagine the can being held up by two opposing crowds. Inside crowd pushing out. Outside crowd pushing in. Normally, it's a stalemate. The can feels squeezed but stable. Then the inside crowd disappears. Of course the can caves. Not because the outside crowd got angrier, just because the balance died. Now bring this back to your room. Your room is not a vacuum chamber. It's filled with air, and the air inside is punching outward on every surface. Walls, windows, ceiling. At the same time, the outside air is punching inward on those same surfaces. And because the air pressure inside and outside are nearly the same, almost always equalized through tiny leaks, vents, cracks, and cause the fact that buildings are not sealed like spacecraft, the forces cancel. So the walls don't implode, not because the pressure is small, but because it is matched. This is a good place to ask the annoying question, okay, but matched how? How does the air know what to do? It doesn't know anything, it just moves. If the outside pressure were higher than the inside pressure, more molecules would be slamming into the wall from the outside than from the inside. Net force inward. The wall would flex inward a tiny bit. The inside volume would shrink. The inside air would get compressed, and the inside pressure would rise. The compression means more molecules per volume, more impacts per area. It self-corrects. If the inside pressure were higher, the wall would flex outward, the air would expand, impacts would thin out, pressure would drop. That's all pressure equilibrium is, a mechanical truce maintained by motion and compression. Now, why don't you implode? Same reason. You are also a pressurized system. Your body is full of fluid, and fluids carry pressure beautifully. Blood, lymph, water in cells, these are not airy sponges, they push back. If you squeeze them, they push back harder. Even your lungs, those seem like empty bags, but they are connected to the same atmospheric pressure through your throat. Unless you're holding your breath with a closed glottis, the air in your lungs is basically at room pressure, so your skin has air pressure outside, and it has fluid pressure inside. They match. You're not resisting the atmosphere with strength, you're matching it with internal pressure. That's why deep-sea diving is dangerous in a way people misunderstand. It's not the pressure itself that kills you. Pressure is fine if you are pressurized too. The danger is pressure differences. The danger is trapped pockets of gas, ears, sinuses, lungs, places where the pressure might not equalize fast enough, or where rapid changes create a mismatch. That's when tissues tear, membranes rupture, bubbles form, not because pressure exists, but because pressure stopped being balanced. So the real villain is not pressure, it's pressure gradient, imbalance. Now, let's deal with the 10 tons number again, because it still feels like a prank. If the air is pushing on a square meter with 10 tons, why don't you feel 10 tons on your chest? Because you also have 10 tons pushing outward from inside your chest area. But I don't have a pump generating 10 tons. You don't need one. Pressure isn't a special substance you manufacture, it's just what fluids do when confined. Your internal fluids are already under pressure because they are trapped in a volume, and because the whole system equilibrated with the atmosphere over your entire life. Here's a thought experiment that forces you to accept it. Take a balloon, inflate it. The rubber stretches because the inside pressure is higher than outside. That pressure difference creates a net outward force on the rubber. Now imagine the balloon at exactly the same pressure inside and out. What happens? It goes limp. Not because pressure vanished, but because the net vanished. The rubber only cares about the difference. Your skin is like that balloon, except your rubber is living tissue, supported by structure, and your inside pressure is tuned to the outside. So you don't feel squeezed, because nothing is trying to accelerate inward. Now, what about windows specifically? Windows don't implode for the same reason. The air on both sides is basically the same pressure most of the time, but sometimes they do flex. You've seen it without noticing what it is. Ever had a door that suddenly becomes hard to open on a windy day? Or you close a window and you feel a little woomph in the room? Or you hear a pop in a building elevator shaft, or in an airplane cabin? Those are tiny pressure differences showing up as real forces. A weather system changes atmospheric pressure by a few percent. A few percent of 10 tons per square meter is still a lot. Enough to bow large window panes, enough to make doors swing, enough to whistle through cracks. But glass is also strong in compression, and windows are supported in frames. And most importantly, the pressure differences in daily life are small and temporary. Now, but wait, if pressure is just molecules hitting things, why is it so steady? Molecules are random. Shouldn't pressure fluctuate wildly? It does fluctuate. On microscopic timescales, the wall is getting uneven punches. One moment a molecule hits here, next moment there. But there are so many molecules, astronomical numbers, that the randomness averages out. The steady pressure you measure is a statistical calm built from insane microscopic chaos. That's a theme in physics that shows up everywhere. Calm on the surface, violence underneath. So now we have the core picture. Air pressure is real, huge, built from molecular impacts. It doesn't crush you because it's balanced by equal pressure from inside you and inside your room. Vacuum doesn't pull. Vacuum removes the inside punches and the outside punches win. Good, but we haven't yet done the most important move. We haven't asked what exactly would happen if the air in your room vanished. Not generally bad. Specifically, because once you can predict that, you truly own the concept. So let's do it. The unfair thought experiment. You're standing in your room, normal day. Then snap, every air molecule inside the room is magically deleted. Perfect vacuum, instantly. What happens? First, the room does not become peaceful, it becomes violent. Because a vacuum is not a new force, it's the removal of the inside punches. The outside atmosphere is still there, still slamming into the outside walls and windows with the same pressure as always. So now the building has a problem. There is nothing inside pushing back, and the net force is inward. If your room were perfectly sealed and you could truly remove the air inside without letting anything leak back in, the outside pressure would try to crush it. 10 tons per square meter doesn't care that your room is indoors. It would press on the walls like a giant hand. In real life, rooms aren't sealed, and you can't delete air instantly. So what you actually get is this: air rushes in through every crack, under every door, through vents, through the tiniest gaps you didn't even know existed. That rushing air is the atmosphere trying to fix the imbalance. And that's why vacuum accidents are not mysterious. They're just pressure doing what it always does, pushing toward the region where there are fewer molecular impacts. Now zoom in on you, because you're also part of the room. If the air around you vanishes, your body doesn't suddenly lose pressure inside. Your blood doesn't instantly depressurize. Your tissues are still pressurized for a moment. So you become briefly the opposite of the room. The room is being pushed inward from outside. You are being pushed outward from inside. Again, not because you have an engine, but because you were equilibrated to 1 atmosphere a moment ago, and now the outside is near zero. The first things to react are the gas pockets. Lungs, sinuses, ears, places where pressure differences can develop quickly. If your airway is open, the air in your lungs expands outward. It wants to equalize. If it can escape, it will. If it can't, that's where damage happens. This is why the real danger in pressure changes isn't the pressure, it's trapped pressure. Then there's the subtler, weirder thing. Liquids start to behave differently. Boiling is not water reaching 100 degrees Celsius. That's another one of those half-truths. Boiling is what happens when the vapor pressure of a liquid matches the surrounding pressure, so bubbles can grow instead of being crushed shut. Lower the outside pressure, and the boiling point drops dramatically. So in a strong vacuum, water can boil at room temperature. Not because it got hotter, but because the outside stopped squeezing the bubbles. And once a liquid starts to boil, it cools itself by evaporation, because molecules that escape carry energy away. So you get this surreal combination. Boiling and freezing can chase each other, depending on conditions. That's not science fiction, that's just phase diagrams and pressure. This is one reason space is such a brutal environment. It's not only no oxygen, it's not only cold, it's that you've removed the atmospheric squeeze that your biology has been quietly relying on. And notice how everything we're saying is the same principle, over and over. Pressure is impacts, balance is stability. Remove one side, and the other side wins. So now flip the experiment. Instead of deleting the air inside your room, delete the air outside your room. Put your intact room in space. Vacuum outside, normal air inside. Now what happens? Now the net force is outward. Every wall, every window, every seam is being pushed from inside by the internal air pressure, with no outside push to balance it. That's an explosion scenario. Not because the air suddenly became strong, same air, same pressure, but now it's unopposed. This is why spacecraft are built like pressure vessels. Not because space sucks. Space doesn't pull on anything. Space just fails to push back. The spacecraft is a container holding in a pressurized atmosphere, and the atmosphere is trying to expand. The hull is what provides the inward force needed to keep that gas from just becoming bigger. Now come back to your everyday life, because this is where the existential part is hiding. You don't feel atmospheric pressure for the same reason a fish doesn't feel water pressure as a crushing event. The fish feels it, but it's not a threat because the fish is pressurized too. Its insides match its outsides. It's adapted to a world that squeezes. You are that fish. You grew up at the bottom of a 10-kilometer high ocean of gas, and you never called it an ocean because you can walk through it. But it behaves like a fluid. It has weight. It has currents. It has waves. Sound is literally a pressure wave. It has storms. It has a surface. And above that surface there's a kind of space. And the 10 tons per square meter is not a gimmick. It's the price of living under that ocean. Now there's a beautiful twist in this. We tend to think of forces as something dramatic. A shove, a pull, an impact you notice. But the dominant force on your body, all day, is this calm, invisible squeeze. Always there, equal in all directions. A pressure bath. So why doesn't it count as a force in your daily intuition? Because your senses aren't built to detect absolute pressure. They're built to detect changes, differences, gradients, motion, damage. If the pressure changes slightly, you notice it. Your ears pop, your head feels weird, your joints ache before a storm. Not because pressure suddenly appeared, but because the balance shifted and your body has to catch up. And that's a deep lesson about physics in general. The universe is full of gigantic quantities that don't announce themselves until they stop canceling. Electric forces inside matter are enormous, but objects don't explode because charges balance. Gravity between you and the earth is huge compared to your muscles, but you don't accelerate through the floor because the floor pushes back. Pressure is in that family. Big numbers hiding behind symmetry. So the next time you're in a room and you look at a window, don't imagine glass holding back a crushing atmosphere. That picture makes the world sound like it's constantly about to fail. Instead imagine two invisible crowds of molecules, one outside, one inside, endlessly pelting the glass. The glass isn't bravely resisting pressure, it's calmly sitting at the boundary of two equal violences. And you're doing the same thing. You are not protected from the atmosphere. You are participating in it. Your body pressure is not a special feature you turn on. It's part of what it means to be alive down here. Life is a pattern that learned how to exist inside a squeeze, which is maybe the strangest part of all. You're not merely in the atmosphere. A big part of you is the atmosphere, temporarily organized. You inhale it, exhale it, swap molecules with it. The boundary between you and air is more like a membrane than a wall. So when we say your room is under 10 tons, the point isn't to scare you. The point is to give you a new sense of where you live, not on a planet, at the bottom of a fluid, held in place by gravity, surrounded by impacts you can't see, and protected, not by strength but by balance. If you want to keep going after this, if you want the next layer of the trick, we can ask a sharper question. Why is atmospheric pressure about 1 atmosphere, and not 10? What sets that number? Why does it fall with altitude the way it does? And how does the molecular picture predict the actual pressure profile of the sky? Because once you see pressure as motion and impacts, the atmosphere stops being air. It becomes a physical object with structure, and then you're not just living in a room, you're living under a sky that has weight.